to go about playing this dot game, okay? So the rules for the dot game, step number 1 is you're gonna check to see, is it ionic, question mark, or is it covalent, question mark? Okay. How do you know if it's ionic? Well, you check the first element and it would have a metal written first. So if it's ionic, then it's going to be a metal plus a non-metal, or maybe you get polyatomic ions in there. Okay? So that's going to be ionic. How do you know if it's covalent? Two what?
Non-metals.
Two non-metals, and then possibly with hydrogen. Hydrogen kind of works like a metalloid too, though, where typically you have to calculate with hydrogen to check to see what your electronegativity difference is between the two. And again, if it's greater than 1.8, then that would actually be ionic. So let's come back to the first page for just a second here. So I forgot about doing that. So we said that nonpolar is when it's equal to 0, and polar is when it's greater than 0 to 1.8. Ionic is when its electronegativity difference is greater than 1.8. Again, there is no fine line to this. This is something that different books do differently. So there is a little bit of gray area with this, but this is what we're going to use. This is what we'll go with. All right. So if it's ionic, what we're going to do is step number 1. We're going to write the charges above each of the ions. And where are you supposed to get the charges from? Well, you look at the periodic table and you look at that little black number right above the symbol. The small black number above the symbol. Okay. And so you're going to write your charges. And then the second thing that you're going to do is you're going to place all of your dots around only the non-metal. Then all dots, usually it's going to be 8, go around only the non-metal. Okay, so let me show you a couple of examples. We'll do a couple of examples on the side here before we do covalence. So I'm going to give you 3 examples that we'll do together. So the first one that we're going to do is NaCl. And I'm going to show you the way that the book teaches it versus the way that I do it. Okay. So for NaCl, I am leaving a little bit of space inside of there. Well, typically what the books say to do is they say to write the valence electrons for each one, and then you show where the electrons are going so that you have a better idea of where it's coming from and where it's going to. So let's look at Na first. How many valence electrons does sodium have? 1. And how many valence electrons does chlorine have? 7. Perfect. Okay. So what we're going to do is we're going to do Na with 1 valence electron, and Cl is going to have 7. So I'm going to go 1, I'm sorry. Let's do 1, 2, 3, 4, 5, 6, and then 7. Do it that way. And what you notice is that the one from the Na, chlorine is more electronegative. Remember, it's under fluorine. So chlorine is the one that's more electronegative. So what's chlorine going to do with sodium's 1 electron? It's going to strip it off. It's going to pull it because it wants to fill in this one space. And so what ends up happening is sodium loses its electron, becoming charged positive, and chlorine gains the electron, becoming charged negative. Okay? I don't care for you to do it this way. All I'm going to say is, we're going to do it backwards, but it's faster. So what I'm going to say is, you're going to write NaCl. You're going to write the charges above each one, so Na is a +1 and Cl is a -1. And then you're only going to put the dots around the non-metal, which chlorine is the non-metal. Okay, let's do this again. So now let's try this for, let's do barium chloride. So barium chloride's formula is BaCl2. So if you have a central atom, then typically it's the one that you have less of. So what we're going to do is we're going to put barium in the middle, and then we're going to put the chlorines around. Typically ionic compounds form what are called crystals. And crystals, you always want positives and negatives alternating. Okay? You won't get 2 positives next to each other, and you won't get 2 negatives next to each other. Why not? They repel. Perfect. Positive, positive, and negative, negative repel, but positive, negative attracts. So we're going to have positive in the middle in this case, and the negatives on the outside. So what I'm going to do is I'm going to put barium in the middle, and then I'm going to do Cl and Cl. So the way that we're going to do this is instead of showing where each one has its electrons, I'll show you after the way that the book would do it. But I'm just going to say what the charges are. So what's barium's charge? Let's take a look back at the periodic table here. Barium's right here, and the charge is what? +2. And chlorine's charge, remember, went 0, -1, -2, -3. So chlorine is -1. Okay? So this is the charges of each one of those. So barium has a +2 charge, and each chlorine is a -1 charge. And now what I'm going to do, I'll do it in a different color so that you can see this. Now what I'm going to do is I'm going to put the electrons only around the nonmetals. Which one's the nonmetal? The chlorine, but I've got 2 of them. So what you're going to do is you're going to put all 8 electrons around both chlorines. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8. Doesn't really matter. I've got 8 going around, so it doesn't really matter how I do it. 1, 2, 3, 4, 5, 6, 7, 8. It looks like barium has 0, but barium doesn't have 0 electrons. It's just that it has 0 valence electrons, but now your next level is filled. Remember, if you look at barium on the periodic table, barium has 56 electrons. So if it loses 2 of its electrons, meaning it has a +2 charge, then how many electrons does it have? 54. But its next energy level is actually filled. It's got 2 plus the 6 again, which gives it 8 beneath that. So it is obeying the Octet Rule again. Okay? So even though it doesn't look like it looks like it's 0 electrons, it still has electrons. So that would be the final thing. Let me show you how the book would do it. The book would do it this way. They would say, we've got barium, and then we've got Cl and Cl around it. Each chlorine has how many valence electrons? I heard this when I was asking for the charge. They each have how many? 7. So I'm going to go 1, 2, 3, 4, 5, 6, 7. And this one also has 1, 2, 3, 4, 5, 6, 7. And how many does barium have? I'll do it in a different color so that you can see the difference. Barium only has 2 valence electrons. So I'm going to put 1 on this side and 1 on the other side just for the sake of this. Who's more electronegative? Who's closer to fluorine? Chlorine. So what's chlorine going to do? Steal the electron. If you notice, there's 1 empty spot on each chlorine. This electron is going to get pulled in by that chlorine, and this electron is going to get pulled in by that chlorine. So really, the end, and then what happens when barium loses its 2 electrons, its charge becomes plus what? +2. And when this chlorine gains 1, it becomes a -1, and this chlorine also becomes what? -1. Okay? My final result looks exactly the same. You don't have to show the arrow, okay? You can do it this way or you can do it this way. I feel like this way is faster. You don't have to check the valence electrons. Most of you already know the charges, so it's easier to just write your charges and then put your electrons around your nonmetal. Good? Okay. That's it for ionics. All right, so now we're going to do covalence. If it's covalent, it's definitely more involved. There are a couple more rules that we need to make sure that we discuss in order to do covalence. So step 2, which is really step 1 again for doing covalence, is what we're going to do is we're going to add up the valence electrons. And the way that we get that is just from the Roman numerals on the periodic table. So you're going to look up your Roman numerals and add up your valence electrons. So we're doing this differently from ionics, okay? So this we could call step 1 for covalence. Once you figure out that it's covalent, you do that. The second thing you're going to do is you're going to arrange your atoms with dashes in between. And a dash will represent, so if you had like X and element Y, a dash actually represents 2 electrons shared between the 2 of them. It's 2 electrons shared between the 2 of them. So the 2 will count for the Y, and the 2 also counts for the X. So there are 2 electrons shared. Sometimes you'll see it written as 2 dots. Okay, it does represent 2 dots. So a couple things with this. The first thing is, your central atom is always going to be the one that you have less of. So typically, usually, the central atom is the one that you have less of. So in other words, if I had something like CO2, carbon would be my central atom. if I had something like NF3, what do you think the central atom would be? The N, okay? So any one that you have that is less than the other one, because there's one of these and two of those, one of these and three of those. So if I had something like CBr4, which one would be the central atom? The C, okay? You're gonna put that one in the middle, and then you're gonna put the other ones around it, all right? You could have more than 4, just so you know there are exceptions, and so we'll talk about those later on. The other thing that I wanted to make sure that you knew was something about hydrogen. Hydrogen is never, ever, ever, ever in the middle. And the reason why is we're going to take a look at 2 things right now. So we were talking about this idea of having 8 and this importance of having 8, and that 8 means that you have a filled energy level. What about helium? How many electrons does helium have? 2. Is helium stable? Yeah. It's a noble gas. That's stable. We know that's one of the noble gases, and that is stable. But remember, our first energy level only has how many electrons in it? 2. So remember, it goes 2, 8, 18, 32. That first level only has 2, and helium is stable with 2. It's perfectly fine that way, okay? And it wants to stay that way. Hydrogen will do 2 things. Hydrogen either can be a +1 charge or a -1 charge. If it's +1, what does that mean? +1 means it loses an electron, and then it has 0. Hydrogen has 1 proton, so it has 1 electron if it's neutral, but if it loses that 1 electron, it now has 0. So what does -1 mean? That it'll gain 1, and then it'll have 2 like helium does. Hydrogen does not obey what is called the octet rule. Instead, what they call it is the duet rule, okay? So if you've ever played in a duet or done a duet before, sung in a duet, then that's just 2, okay? So hydrogen is actually fine with just the 2 electrons. So hydrogen is never in the middle, and hydrogen never has any more than 2 dots or 1 dash. So you'll never have dots around hydrogen, and no dots on the H. You'll have a bond, and that's all you'll have. Okay, you'll just have a bond, unless it's completely alone, which is not going to happen in nature. All right, and then once you have that, the very last thing that we're going to do is we're going to start putting our dots all around. Okay, so we've arranged the atoms, we put dashes in between them. We know that hydrogen is not in the middle. Your central atom is the one that's less. And then the last thing is we're going to start putting our dots first around the outside atom and then around the central atom. So place dots first around the outer atoms, then on the central. And if there is any funniness, I'm going to call it funniness, any strange anything that happens, then it's applied to the central atom. So if you're babysitting, and some of you may know this to be one of those like just underlying rules of babysitting. If you're babysitting a bunch of kids, and so let's say that there are like 4 kids that you're babysitting, and they order a pizza, and a pizza has 10 pieces of pizza in there. And they say, whatever, you know, go ahead and just feed the kids. Before you get to eat pizza, what do you need to make sure of? That all the kids ate. And they're all happy and content with their pizza, okay? If there's no pizza left, you don't get any unless one of the kids decides to share with you and says, hey, listen, I already got these pieces, let's share, you can have some of mine, okay? And that's where sharing is going to come in, and we want to make sure that everybody obeys the octet or the duet rule. So right under here, let's talk about that, but you need to make sure you take care of the outside atoms first, and then you're going to take care of the central atom. If there's anything weird, in addition to maybe there's extra pizza, guess who gets it? You do, okay? Central atom will get, if there's any extra, you actually can get that. So if there are any extra electrons, it's the central atom that takes it, not the outside atoms. The outside atoms will all do 8 maximum, or 2 if it's hydrogen, okay? So, in really big letters, I want you to write the octet rule. Okay. The octet rule basically states that atoms will lose or gain electrons to acquire stability with 8 electrons in their outermost shell, in the outer shell. Okay, so they'll try to get 8. And then right under it, I'm just going to write, smaller, the duet rule. And the duet rule is basically just that hydrogen and helium are happy with how many? 2. Are stable with 2 valence electrons. Okay, they're stable with 2 valence electrons. All right, and the last thing is special cases. You can have what are called double or triple bonds, but I want to show you that later. So, and then we'll come back to boron and aluminum also. So let's flip to the next page. So there is what is called the pizza rule. We'll talk more about this later on too. But it's basically what I use to determine whether a molecule is polar or nonpolar. And so the bond type you have to calculate to see. So you're going to subtract the electronegativity differences. But as far as figuring out the molecule type, you want to look at it. And if you look at the center of your pizza and you see pepperonis going all the way around, and that's all you have are pepperonis going all the way around and they're equally spaced, we're going to say that it's equal and it's non-polar. But let's say that you have pepperonis on 3/4 of it, and then you've got anchovies, something crazy like that, on the other quarter of it. It's not equal going all the way around, and so then what we say is we call that polar. And the reason why is, what happens is, in a molecule, they're going to be pulling on the electrons. So the elements are going to be pulling in different directions. And the ones that are more electronegative will do what? They'll pull more on the electrons, okay? Now, they're not going to completely take them away unless they have an electronegativity difference greater than 1.8 is what the books have kind of defined this as. But if you calculate your difference and you get 0, they're just going to sit there and share forever. But if there's anything different where their electronegativity difference, there's a difference greater than that, then you're going to have a polar molecule. So I said you throw in an anchovy, you have unequal sharing of the electrons around the central atom, whereas if it's nonpolar, all of your pepperoni is equally spaced and there's equal sharing of the electrons around the central atom. Ionics are not molecules. They don't share electrons. Remember, these are not sharing. So they're not supposed to be sharing the electrons. So if it's ionic, it doesn't apply. In other words, if you have a metal plus a nonmetal, we're just going to call that ionic. And we're not going to even worry about doing our electronegativity difference, a calculation of it. So let's try 3 of these and see how we do on the dot game. Okay? So here we go with the dot game. First question is, question number 1 is it ionic or is it covalent? Okay? Is this a metal with a nonmetal?
No.
No, and you really only need to look at the first element, because if the first element's a metal, it's probably going to be ionic. So we know that this is covalent. Okay, we've got covalent. It's diatomic. Perfect. So the second step is, what we're going to do is, if you look back at your rules, it says, step number 1 was ask if it's ionic or covalent. Step number 2, what do? If it is covalent, we add up our valence electrons, then we're going to arrange our atoms with dashes, and then we're going to place the dots around the atom. So we're kind of going to do all of these at one time now. So let's add up our valence electrons. Chlorine is under fluorine, and how many valence electrons does that have? 7, but there are 2 of them. So I'm actually doing 2 times 7, which gives me a total of 14 valence electrons. So that 14 goes right there for the valence electrons. So what I'm going to do is now I'm going to arrange my atoms, and you put a dash in between the 2 atoms. And this dash right here is representing 2 shared electrons. And it actually applies to this one and it applies to this one. Okay? We know how to count by even numbers, and so you're going to go 2, 4, 6, 8, 10, 12, 14, 16, and so on. Sometimes you have to get up to 48. Sometimes you have to go up to 60. So we're going to add our valence electrons first to the outside atoms and then to the central. Is there a central atom here? No. So that doesn't really matter. It doesn't really matter which one we start with. I'm just going to say 2 in the middle, and then I'm going to start going up to 14. I'm not going to count backwards. You can if you want. I think it's easier to start at 2, and then I'm going to go around and I'm going to put my dots around until I get to 14. This counts for the central one on both of these, okay? So it goes 2, I'm going to put 4 there, 6, 8, 10, 12, 14. Then you're going to check to see if you obey the octet and the duet rule. Well, I don't have hydrogen here, so I'm not worried about the duet rule. But how many electrons does this one have going all around it? Well, that's 2, 4, 6, plus this 2 makes it 8. That checks. This is 2, 4, 6, plus that is another 2, so that makes it 8. These both obey the octet rule. So yes, we're obeying the octet rule. Let's try the next one. Oh, polar, nonpolar. So if this is diatomic, we've got perfect equal sharing. It doesn't matter what the value is. This ends up being equal sharing, which we call nonpolar. Perfect. Okay, let's try the next one. HBr. Okay, so we know that H falls under what, typically? Under covalent. We can do a calculation just to make sure. So I'm going to take a look at my electronegativity difference for this. And H says 2.1. And BR says 3.0. So if you subtract, its absolute value of it, what's the difference between 2.1 and 3.0? 0.9. Perfect. It's 0.9. So my difference, my ED, is equal to a 0.9 difference. And if it's 0.9, what does that make it? Not ionic, but polar covalent. Perfect. But that's the bond type, so I need to make sure that my molecule type is right. So my bond is definitely going to be covalent. I know that it's covalent. So if it's covalent, that was step number 1. Step number 2 is add up my valence electrons. How many does H have? 1. And how many does Br have? It's under fluorine. 7. So we have a total of 8. Perfect. So let's write 8 where it says valence electrons. We're going to put a dash in between the two of them. So I've got H dash Br. Again, this represents 2 electrons already, okay? And the 2 electrons are shared between both of those. So how many does H have? 2. Does H need any more than 2? No. H is done. It's already obeying the duet rule, okay? So now guess where the other 6 electrons go? Around the Br. So I've got 2, 4, 6, 8, and it's done. Let's try the next one. Oh, polar, nonpolar. This is not equal, so they're not poling the same. If it's unequal sharing, then we call it polar. Okay? You'll see when it happens where we need to use the pizza rule. So now let's try NH3. So again, first step is let's figure out if it's polar or ionic. So we know it's not ionic. Why? Yeah, perfect. There's no metal there, so we're going to call this covalent. All right, and then let's, number 2, add them up. So nitrogen on the periodic table is how many? 5, perfect. Plus each hydrogen has how many? 1. So we have a total of 1 times 3. You can just write plus 3. So if you add them up, you get 8 again. So now we're getting 8. Who goes in the middle? N. Just like when we did organic naming, you can basically make like a plus sign going around it, but we only have 3 H's. So I'm going to go N dash H dash H dash H to get 3 of them going around. What do you know about the H? It only wants 2, and this one has 2, and this one has 2, and that one has 2. So my H's are all set, but I need to get to 8. So I go 2, 4, 6. Guess where the last 2 go? On top of the nitrogen. Awesome. Okay. Now, to figure out what type of molecule this is, what we're going to do is, if there are dots on the central atom, it automatically makes it unequal. So that was one of the things from the first page. So we're actually going to call this polar. Okay? And then we're going to do a continuation of this after. We'll talk about double bonds, we'll talk about triple bonds, but this is a good intro to